For having me here. I was already here. My talk is entitled Ramsay Theory on Diffsequences, and this is work in arithmetic Ramsay theory, loosely inspired by Vandervaren's theorem. So just kind of the general spirit of Ramsay theory, you have 6 people in a room, every pair of them either know each other or they don't, and you'll see that, oh, 3 of them know each other or 3 of them don't know each other. So one slogan you see to summarize this is that complete randomness is impossible. Here's another slogan that I kind of like a bit better. If you divide a whole into parts, is one of the parts guaranteed to retain some special structure? So if I color the edges of my clique, is one of the color classes going to still have a pretty big clique contained in it? So today we're not going to be coloring any edges. We are going to be coloring positive integers. So let's start with a big bold claim about the positive integers, which is that they contain arbitrarily long arithmetic progressions. Now, if you partition them into 2 disjoint sets, will one of these parts, or one of these colors, still contain arbitrarily long arithmetic progressions? Or what if we have 3 colors, or 4 colors, or any finite number of colors? And the answer to this question is yes, no matter how many colors you have. So this is a classical result from Vandervaren. Not the earliest result in Ramsay theory. It's predated by Schur and maybe even predated by Hilbert's cube lemma, if you want to count that. But definitely this kind of kicked off the field. So given positive integers k and r, there exists some natural number n such that any r coloring of 1 up through n includes a monochromatic KAP. Or alternative way of phrasing this is that if you color all the natural numbers with r colors, you're going to get arbitrarily long monochromatic arithmetic progressions. So, but here's this n in the way that I've written it here. So you might wonder what the smallest such n is. And this is what we define as the Vandervaren number WRK. Now, WRK, for very tiny r, like 1 maybe, and for very tiny k, you can compute for infinite families. But other than that, it's only known for a few values. But we don't really care about specific values. We care about having nice bounds. So the best known upper bound for general r and k, this is due to Gowers. WRK. This is not really relevant to my talk. I'm just writing it because it's cool. It's at most 2 to the 2 to the r to the 2 to the 2 to the k plus 9. That's probably pretty far from the truth. There was a breakthrough made on off-diagonal Ramsay numbers, not Ramsay numbers, Vandervaren numbers by Ben Green in the past year or so. But the I'll just write the best known bounds for 2 colors. So this is due to Berlekamp. And this is only going to be for k prime because it comes from some sort of finite field construction. So we see there is not a tower. And in fact, Ron Graham conjectured that for 2 colors, we have W2k is at most 2 to the k squared. And while his related conjecture for the off-diagonal version was false, I believe this is still open. So that's if you want to think about Vandervaren numbers. We're just going to do a quick example, just make sure everybody's comfortable with the flavor of the question. So in general, how do you find WRK? Well, for the lower bound, you need to find some coloring of 1 up through WRK minus 1 such that you can avoid monochromatic KAPs. And then you have to show that if you're actually going up to WRK, you can't do such a thing. So let's look at W2, 3. So we're trying to find the smallest n such that any 2 coloring of 1 up to n contains a monochromatic 3AP. So for the lower bound, I present to you 8. So 1, 4, 5, 8, I'm going to color those red. 2, 3, 6, 7, I'm going to color those blue. And we observe that there's no red 3AP, there's no blue 3AP. Now, let's try to do the same thing for 9 and see what happens. So here's the numbers 1 through 9. My goal, which we already kind of know is impossible, but we'll see why it's impossible, is to try to color these in a way that we don't get any monochromatic arithmetic progressions of length 3. So 4 and 6, I have to start somewhere. I either have to make them the same color or make them different colors. So let's assume that 4 and 6 are both red. Now, we don't want 4, 5, 6 to be a red 3 AP. So let's say 5 has to be blue. We don't want 4, 6, 8, so 8 has to be blue. We don't want 2, 4, 6, so 2 has to be blue. And now you see that we failed because in our efforts to avoid a red 3 AP, we've gotten stuck with a blue 3 AP. So let's start over. Let's try 4 and 6 to be different colors. And now by symmetry, let's just say that 5 is also red. Now we're going to play Sudoku in the sense that every choice I make from here on out is predetermined by these 3 choices. So 3, 4, 5 can't all be red. 3, 6, 9 can't all be blue. 1, 5, 9 can't all be red. 1, 2, 3 can't all be blue. And 2, 5, 8 can't all be red. And now we're stuck because look at 7. If 7 is blue, we get a blue 6, 7, 8. If 7 is red, we get a red 5, 7, 9. So we've now established the upper bound of 9. So this is really the last part of the talk that's about arithmetic progressions. But what I will be talking about is, can you make these Vandervaren type results for different types of arithmetic structures? And kind of the story goes, as far as I understand it, is that maybe what's a natural strengthening of Vandervaren's theorem is to say, instead of my coloring guaranteeing arbitrarily long arithmetic progressions, I could say my coloring guarantees arbitrarily long arithmetic progressions that only have certain differences. So this kind of produced this notion of an R large set, which is a set such that if I have any R coloring of the natural numbers, I'm guaranteed to have arbitrarily long arithmetic progressions whose common difference is in my set. So Vandervaren's theorem is just to say the set of all positive integers is R large for every R, and you can restrict this concept further. But then, after you restrict this concept, you can also weaken this concept and say, I'm still going to have a set of prescribed differences, but I don't care if all the differences in my sequence are the same as each other. So this is a diff sequence, and it's kind of, you can think of it as being like 2 steps away from the original question. So this is due to Bruce Landman and Aaron Robertson, and they said a d-diff sequence, so you fix your infinite set of positive integers, and a d-diff sequence is an increasing sequence where all the consecutive differences, which I'll sometimes refer to as the gaps, are in your set D. So we don't care about them being the same as each other, but we do care about them being in this prescribed set. So here's my example. So let's say D is the set of powers of 2. Then this is a d-diff sequence because 11 minus 3 is a power of 2, 15 minus 11 is a power of 2, 23 minus 15 is a power of 2, 27 minus 3 is not a power of 2, but we don't care because we only care about the consecutive differences. And this is 6 numbers, 5 gaps, 6 numbers. We call this length 6. Okay, so we have this notion of a diff sequence, and you might ask something about coloring. Are we going to get arbitrarily long monochromatic diff sequence? Like, can we get analogous results to Vandervaren's theorem? So here we have the notion of R accessible. So we say that a set D is R accessible if any R coloring of the natural numbers contains arbitrarily long monochromatic D diff sequences. And here I have an equivalent definition. You can kind of just think of this as the finitary version. So you're R accessible if for every k there's some n such that any R coloring of the numbers 1 up to n contains a monochromatic d-diff sequence of length k. So let's just do a few examples to make sure everybody's on board with the definition of R accessible. So here's my set D. It's going to be the set of all even numbers, or I guess all positive even numbers. And D is going to be R accessible for any R. And why is this? Because R is finite, so we color the natural numbers with a finite number of colors. So some color class is infinite, and that color class is going to contain either infinitely many evens or infinitely many odds. So within that color class, I have arbitrarily long sequences where the gaps are all even, so I have arbitrarily long monochromatic d-diff sequences. Next, let's consider something that's not accessible for a lot of colors. So here's a set of odd numbers. It's 1 accessible because everything's 1 accessible, but it's not even 2 accessible. And since it's not 2 accessible, it's certainly not going to be 3 accessible or higher, because I can just kind of take a very lazy 3 coloring where I just never use the 3rd color, and then the first 2 colors just be whatever my avoiding 2 coloring was. So why is this not 2 accessible? Well, let's say we color all the even numbers red, we color all the odd numbers blue. If you look at one color class and you look at some D-diff sequence within that color class, well, all the gaps are even, and you don't have any even gaps. So forget arbitrarily long D-diff sequences, you're not even going to get a monochromatic D-diff sequence of length 2. And let's just do maybe one more example that involves this additional definition. So once you have this notion of R accessible, that's like saying I have something that looks like Vandervaren's theorem. And if I have something that looks like Vandervaren's theorem, I can ask, well, what are the things that look like Vandervaren numbers? So here, if I have an R accessible set D, I can define this delta dkr as the smallest n such that any R coloring of the numbers 1 up through n is forced to contain a monochromatic D-diff sequence of length k. So first example I'll give you, suppose that D is the set of multiples of 5. I just will assert for you that this is 3 accessible. It turns out to actually be accessible for any number of colors, but let's just stick with 3 for the time being. So I'm going to claim that delta dk3, which is now well defined because we're talking about a 3 accessible set, has this upper bound. And where does this upper bound come from? Well, I have 15 types of numbers. I have 5 residue classes mod 5. I have 3 colors. And here you can see by pigeonhole that I'm going to have k numbers that are the same type. So because of the same type, they're the same mod 5, so their differences, their gaps are all multiples of 5, so the gaps are all in D, and they're the same color. So that's a monochromatic D-diff sequence of length k. And the argument I just told you does not depend on 5, it does not depend on 3. So in fact, if dB is the set of all the positive multiples of B, then this is going to be R accessible for any number of colors, and you see this upper bound here that you can similarly prove by pigeonhole. So if you scour the literature, you might find some other examples where delta exists and it's bounded above by something linear. And you might find some more examples where the bounds aren't linear, but they're polynomial. So one question you might be inclined to ask is, if delta exists at all, so if delta is R accessible, sorry, if D is R accessible, is delta dkr always just going to be polynomial in K? And the first half of the rest of my talk is to establish that no, it is not. So what I'm going to focus in on is letting D be the set of powers of 2. And there's nothing inherently special about the powers of 2, but this is just going to be used as a proof of concept that it's possible for delta dkr to grow faster than any polynomial. So here, just to shorten the notation, I'll say that delta of k is going to represent delta dk2, where D is the set of powers of 2. And now pretty much the rest of my talk, we're only going to be thinking about if you have 2 colors. So what was known about delta of k previously? So it was first studied, of course, by Landman and Robertson. And they had this periodic coloring mod 8 that they used to get a linear lower bound. And they established that it was actually 2 accessible using this induction argument that gave this exponential upper bound. So pretty big gap between a linear lower bound and exponential upper bound. A few years ago, some of my collaborators, we pushed the linear lower bound up to a quadratic lower bound. But in the grand scheme of things, not really a big deal because you still have this gap between polynomial and exponential. So what I did is, during part of my thesis work, is I showed that in fact delta of k is bounded below by this monstrous thing. The key part is the 2 to the root 2k, so in fact let's just change it to that. The individual terms don't really matter. The point is that this is at least exponential in the square root of k. So while there is still a gap between exponential and square root of k and the upper bound exponential in k, we've now established, I believe for the first time, that in a diff sequence setting, sometimes delta grows faster than polynomial. If you're wondering about like what the real answer is, well, the first thing I'd say is I don't know. But as far as the computations, I know the values for k up to 12, and they track pretty closely to this lower bound here. So if I had to guess, I would think it's probably the right exponent, but 12 is not a big number, so anything can happen, I suppose. All right, so before I go into the proof of this, I do want to just review the upper bound of 2 to the k minus 1. And part of that is because if you don't establish this upper bound, or at least if you don't establish that there is an upper bound, then maybe delta is infinite, maybe it's not really too accessible, maybe we're just speaking nonsense. So let's make sure we're actually talking about a too accessible set.
So before that, I have a question. Is there a characterization at all for D being R-accessible or even too accessible?
I don't think there's a general classification, but the second part of the rest of my talk is about that type of question. Okay, so why is this 2 to the k minus 1 the upper bound? So we're going to proceed by induction. K equals 1 is trivial. So now the induction step is that if I color the numbers up through 2 to the k minus 1 with my two colors, I am going to get some monochromatic diff sequence of length k. Say that ak is the biggest number in that diff sequence. And for the sake of contradiction, let's pretend that I don't end up getting to k plus 1. So let's say a1 through ak are all red. If I'm not going to get length k plus 1 monochromatic diff sequence, then ak plus 1 can't be red. ak plus 2 can't be red. ak plus 4 can't be red, ak plus 8, etc. So I have a whole bunch of numbers, ak plus any power of 2, that need to be colored in the other color. And let's just stop at 2 to the k plus 1 minus 1. So we see that in that range, we have ak plus 1, ak plus 2, all the way up to ak plus 2 to the k. So there's k plus 1 numbers that I've had to color the other color, say blue. But if you check what the gaps are in this case, the ak's all cancel out. We're just left with powers of 2. So it's kind of similar idea as before. In our efforts to avoid extending the red monochromatic diff sequence, we got stuck with a longer blue monochromatic diff sequence. So that completes the induction. Now for the lower bound. So here, I'm going to make use of a series of periodic colorings, and I'm kind of over the red and blue thing, so we're just going to use color 0 and color 1. So the first periodic coloring I'm going to use is P1. So P1 just means you're coloring according to parity. So when I say the repeating block is 1, 0, I just mean 1 is color 1, 2 is color 0, 3 is color 1, 4 is color 0, etc. So why is this a good start? Well, we're trying to avoid long monochromatic sequences where the consecutive gaps are powers of 2. And at the very least, what we've done here is we've made it such that since you're alternating, x and x plus 1 are always different colors. So at least I avoided gaps of size 1. That should count for something. So now let's take it a step further and introduce this other coloring, P2. So P2 is going to be a periodic coloring mod 4. And where did it come from? Why this coloring mod 4 as opposed to another one? Well, the idea is that the first half of the repeating block 1, 0, 0, 1, that's just copied from the line above. And the second half is the complement. So I have 1, 0, and then I have 0, 1. And why do we do that? We do that so that by design, x and x plus 2 are always going to be different colors. So we've now avoided gaps of size 2. But here, the key is that we've also restricted the number of gaps of size 1. So regardless of how long your monochromatic D-diff sequence is with respect to the coloring P2, you're going to have no gaps of size 2 and at most one gap of size 1. So we'll extend this table a little bit, but this last column is going to be the key, where your bound on the number of small gaps is going to be a constant. We have P3. So P3 is going to be a periodic coloring mod 8. So the repeating block is 1, 0, 0, 1, 0, 1, 1, 0. So where is that coming from? 1, 0, 0, 1, I copied the previous line. 0, 1, 1, 0, you can think of that as like the bitwise complement.
That is Theorem was a sequence, isn't it?
Yeah, so it turns out if this pattern here, I'm going to keep going, so I'm going to have this coloring PT, where PT, the first half is just PT minus 1, and the second half is just the complement. And this is, in fact, the first 2 to the t bits of the 2 Morse sequence.
Right.
So here, so this just means that if you're 1, 4, 6, or 7, mod 8, you get color 1, otherwise you get color 0. And by construction, x and x plus 4 are always going to be different colors. So if you look at just the monochromatic D-diff sequence, you avoid gaps of size 4. And importantly, we also limit the number of smaller gaps. So regardless of how long your monochromatic D-diff sequence is with respect to P3, you're going to have at most 1 gap of size 1 and at most 2 gaps of size 2. So as I already said this part, we can recursively come up with the next coloring, which is just the mod 2 to the t periodic coloring. And it's going to always avoid gaps of size 2 to the t minus 1. And it's going to limit the number of times each smaller gap occurs. And just to quantify what's happening, because maybe it's not enough to infer from a few rows of the table, that ultimately what we're going to see is with respect to PT, you're going to have at most 1 gap of size 1, at most 2 gaps of size 2, at most 3 gaps of size 4, at most 4 gaps of size 8, etc., all the way up to at most t minus 1 gaps of size 2 to the t minus 2. And that's going to be this key lemma here. So with respect to the coloring PT, just some notation, I'll say that a short gap is anything less than 2 to the t minus 1. So that's what I was trying to limit in the last column. And a long gap is going to be anything that's at least 2 to the t. And when I say these gaps, I'm really talking about the gaps in whatever specific monochromatic D-diff sequence I'm looking at. So all the gaps are powers of 2. And we said we've avoided gaps of size exactly 2 to the t minus 1. So they're not classified as short or long because they don't happen anyway. So what I want to do here is I want to quantify just how few short gaps we have, because if I have a sequence of length k, it's going to have k minus 1 gaps. So if I don't have a lot of short gaps, I'm going to be forced to have a lot of long gaps. And that's going to force my numbers in my sequence to be pretty big. So here's my lemma. So if we color the integers with respect to PT, then no monochromatic D-diff sequence is going to have more than m plus 1 instances of 2 to the m, or m up to t minus 2. So at most 1 of size 1, 2 of size 2, 3 of size 4, etc. And now if you add up over the different values of m, we get that there's at most t squared minus t over 2 short gaps. So let's hold off on the proof of this lemma for a bit. But what does this lemma do for us? It gives us a lower bound, it gives us an upper bound on the number of short gaps that does not depend on the length of the sequence, but there's k minus 1 total gaps. So we do get a lower bound on the number of long gaps that does depend on the length of the sequence. So ak minus a1, like the last term of your sequence minus the first term, is the sum of the gap sizes. So we can get a lower bound on the sum of the gap sizes because, let me try to use the pointer. This is the minimum size 2 to the t of a long gap. And this is the minimum number of long gaps. So what I've shown here is I've shown a lower bound for the sum of the long gaps, which is a lower bound for just the sum of all the gaps. So I promised you that we would grow faster than polynomial in k, and if you look at this, it just grows linear in k. So maybe I lied to you. But the good thing is that this is true for any value of t. So you can just pick the t that makes this linear lower bound the best. So in practice, that's when you take t to be about the square root of 2k. So I won't go into the details of the computation, but once you have this coloring idea, once you prove this lemma, then it's just a lot of addition. I will say that this argument with the PTs, it's not quite what gives you the original lower bound that I wrote. If you refine this a little bit more, you can get an extra factor of root k, but I mostly just care about the 2 to the root k. So the fact that you get an extra multiplier of root k isn't a big deal. But how you do get that extra multiplier of root k is the idea is instead of just considering this simple coloring pt, you can consider what I call pt comma u. So we have this extra parameter. And what is pt comma u? The idea is take your coloring pt and replace every bit with 2 to the u copies of itself. So if this is p2, it had the repeating block of 1, 0, 0, 1. I'll say that p2 is also what I could call p2 comma 0. And if you want to see what is p of, say, 2 comma 2, well, I'm replacing every bit with 2 to the 2 copies of itself. So now my repeating block would look like this. And as it turns out, since I have this extra parameter to vary, I'm able to get a slightly better bound. All right, so where does this lemma that's limiting the number of short gaps come from? So I'm not going to go into the entire argument, but I will provide some important bits. So first thing to note is we're going to address one m at a time. So you can think of, if you have pt, you have this your repeating block is size 2 to the t. So each repeating block of size 2 to the t can be divided into a bunch of subblocks of size 2 to the m plus 1. And if you look locally at a subblock of size 2 to the m plus 1, it looks exactly like the repeating block for the coloring pm plus 1. But if you remember, the coloring pm plus 1 avoids gaps of size 2 to the m. So if ai minus 1, and let me not get ahead of myself. So just to make it easier to say what I'm going to say next, we'll consider any residue from 1 to 2 to the m as being in the first half mod 2 to the m plus 1, and then everything from 2 to the m plus 1 to 0 as being in the second half. And the point is, since a subblock locally looks like pm plus 1, if I have ai and a minus 1, they can't actually be in the same subblock because the coloring pm plus 1 avoids gaps of size 2 to the m. So if I have a gap of size 2 to the m, what I have to be doing is I have to be going from the second half of a subblock to the first half of the next subblock. So let's make sure everybody's on board with that, because this is a pretty important observation. So here what we're trying to do is we're trying to limit the number of gaps of a certain size. So if I only have one of a certain size, then I've already succeeded. So let's assume I have more than one gap of a certain size. Well, I can't have the same size happen twice in a row because I'm going from the second half to the first half of the next subblock. Well, now I'm in the first half of a subblock, and every gap of this size starts in the second half of a subblock. So I somehow have to add some other gaps to get back to the second half of some subblock before doing another 2 to the m. But if I'm adding longer gaps, they're bigger than 2 to the m, they're divisible by 2 to the m plus 1, they're just going to take me from where I am in my subblock to the same place in a different subblock. So if I want to move to a different place within my respective subblock, I need to use smaller gaps. So if I use my 2 to the m and I get from the second half to the first half, and later on I want to use another 2 to the m that starts in the second half, I need to somehow in between use some smaller gaps to get myself from the first half back to the second half. So that means between every 2 gaps of the same size, there's a gap of smaller size. So let's think about this. Between every 2 gaps of size 1, there's a gap of smaller size. But there's no size that's smaller than 1. So you don't have 2 gaps of size 1. So you have at most 1 gap of size 2 to the 0. And now between every 2 gaps of size 2, there's a gap of smaller size. So between every 2 gaps of size 2, there's a gap of size 1. but there's only one gap of size 1 total, or maybe there's none. So there's at most 2 gaps of size 2. So then you might get excited and you might think, okay, well, between 2 4s, there's either 2 or 1, and there's at most 3 1s and 2s, so there's at most 4 4s. Issue is, so far we're good on 1s, we're good on 2s. The lemma says that there's at most 3 4s. So if you're just using this heuristic that you never have like 2 of the same size without something smaller in between, you might think it's possible to get this thing with 4 4s. 4 2, 4 1, 4 2, 4. You see between the 2s there's a 1. Between every pair of 4s there's either a 1 or a 2. But this is also actually impossible. And the reason that this is impossible is because when I've been focusing on the fact that between every 2 there's something of a smaller size, we've kind of lost some information there. It's not just that there's something of smaller size. There's enough things of smaller size so that when you add them up, it takes you from the first half of a subblock back to the second half of some subblock. So if you want to have a lot of gaps of size 2 to the m, in particular if you want to have more than m plus 1 instances of 2 to the m, you're using smaller sizes to switch between the second half and the first half quite a lot of times. So the sum of the smaller gap sizes has to be pretty substantial, but by induction we have an upper bound on the number of gaps of each smaller size, and if you check the computations, the sum just can't be big enough to switch halves enough times. So that's all I'll say about this lemma, so I know it's not the full proof, but then this kind of fills in the missing pieces of how we got this better than polynomial lower bound for delta of k. So what's next for this type of problem? So the more quantitative side of things where you're looking at analogs of the Vandervaren numbers. Well, for the powers of 2, my lower bound is on the order of 2 to the root k. The upper bound is on the order of 2 to the k, and quite stubbornly, there's nothing really that I know that's better than the basic induction argument. So there seems like quite a lot of work to be done on the upper bound in trying to pin down what's the correct asymptotic for powers of 2. But then you could also make the case, as I'm kind of inclined to, that like powers of 2 aren't really important. The reason I'm talking about powers of 2 is they provided this proof of concept about the possible behavior of delta, that delta is not always polynomial. So what we can instead ask is just in general, what are the possible behaviors for delta? If I have some R accessible set D, what does this function delta dkr look like? We know it can be polynomial. Now we know that it's possible to be exponential in root k. Is it possible to be faster than that? Is it possible to even be exponential in k? So kind of the big question I would say on this type of problem is what are the possible behaviors for delta as just a function of k? But now the rest of my talk, I'll talk more about what Hong asked about, what is 2 accessible. And actually kind of how I pivoted into that is I was trying to answer this question about the growth. And one interesting fact about Diffsequences is if your set D is just some different set t minus t, I guess all the positive differences, then that set is going to be R accessible for any number of colors. And that means you can have arbitrarily sparse sets that are still going to be R accessible. So you might think if I have a really sparse set, that's going to give me really big numbers for delta. That seems like a good sign. In practice, I haven't had any success with that approach because the really big numbers are just slower growth with massive constants. They're not actually faster growth. So then I thought, ooh, maybe I can get some faster growth by looking at factorials. And I think I got some pretty big lower bound. I think I might have even had a factorials in my lower bound for delta when D was the set of factorials. But the problem is delta doesn't exist when D is the set of factorials because the set of factorials is not even 2 accessible. And then that's kind of how I got into the next question of thinking about what's 2 accessible. But just to review a bit, we just talked about powers of 2, and they're 2 accessible. And powers of 3 are not. So you might think, oh, maybe I can get a slightly better constant in my exponential root k by looking at powers of some other integer. And you can't. Well, what's wrong with powers of 3? They're all odd. The first example I gave you is that odd numbers are not too accessible. So some subset of them is certainly not going to be too accessible. And in fact, we can take this a step further. The set of powers of t is never going to be too accessible except for t equals 2. And that's just because all the powers of t are 1 mod t minus 1. So you can take a periodic coloring mod t minus 1, for example. Maybe you color all the multiples of t minus 1 red, and you color everything else blue. As you're moving along in your diff sequence, every time I'm adding a number that's 1 mod t minus 1. So I'm always just moving to the next residue class. Eventually, I would hit all the residue classes. I'd be forced to hit both colors. So here we see that periodic colorings get the job done. So I know about exponential sets. I know about factorials. So the first result I kind of proved of this nature is that the set of factorials is not too accessible. And I'll talk about that in a little bit. But then I wanted to kind of unite this to the results about exponential sets. And the idea is, well, what do these have in common? What they have in common is that each term in my set is a factor of all the bigger terms. So generally what you can think of is you have some integer sequence, positive integers, where aside from the first one, they're not going to be 1. And you consider this set D sub an that consists of a1, a1 times a2, a1 times a2 times a3, etc. And I originally wanted to call this set factorials, but I decided to call it a dividing set just because each term divides the next one, and because of that, each term divides all the subsequent terms. And what I was able to do is I was able to classify when a dividing set is too accessible. So far, the only example we've seen that is if it's just the powers of 2. But the classification is that the dividing set is too accessible if and only if this underlying sequence an contains arbitrarily long strings of consecutive 2s. So with powers of 2, I'm multiplying by 2 every time. We don't need to multiply by 2 every time. I can maybe start with 1, multiply by 2 like 20 times, then multiply by 3, then multiply by 2 like 50 times, then multiply by 3, multiply by 2 a million times, multiply by 3, keep going and have longer and longer streaks of 2s, but maybe occasionally interrupt it. That should still be too accessible, but pretty much anything else you think of will not be. So why is this the case? So here I'm maybe not going to go through all of this. So why is a dividing set where the underlying sequence has arbitrarily long strings of consecutive 2s? Why is it too accessible? This is actually just rehashing the argument that we used to show that the powers of 2 were too accessible. The idea is, for the sake of contradiction, assume that it's not too accessible. So assume that there's some annoying coloring that makes it so you can't do anything better than length k. So you can't do anything better than length k. So you actually do have some sequence of length k, say a1 up through ak. And now, because I have arbitrarily long strings of consecutive 2s in my underlying sequence, then my set includes some constant c, where I have c, 2c, 4c, etc., all the way up to 2 to the k times c in my set. And I claimed that length k was the best I could do. So if I don't want to extend that length k sequence, I have to make ak plus c, ak plus 2c, etc., all the other color. And if I do that, I end up giving myself a length k plus 1 sequence in the other color. So it's the same contradiction as before.
Wait, maybe I have a very silly question. Why do you have to go all the way to 2 to the k here? What if you just have k, then you have a blue sequence of rings?
It's c, comma 2c, comma 4c, not comma 3c. So there's only k plus 1 terms that I've given you here. It's a geometric sequence. The stuff I'm adding.
Oh, I see. So.
Yeah.
Oh, right,
there's no
right,
3c.
Right. I see. Okay.
Yeah, so I try to avoid k plus 1 red, I get stuck with k plus 1 blue. And now the rest of the talk will just focus on the other case, which is trying to show that pretty much anything else, so anything that doesn't have this arbitrarily long strings of consecutive 2's, then the corresponding DAN, the dividing set, is not going to be 2 accessible. So what do we know so far? We know that powers of 3 or powers of 4 or whatever, these are dividing sets that are not 2 accessible, and that rested on there being some sort of periodic coloring. Now, if you try to use a periodic coloring for something like factorials or one of these other dividing sets, it's not going to work. So we have to come up with a new idea. So I try to think of the closest thing I could think of to a periodic coloring, which I call a quasi-periodic coloring. So the idea here is for every dividing set DAN, except for the ones we just dealt with on the previous slide, we're going to associate it with some irrational number alpha. And we're going to color all the numbers according to the parity of the floor of n alpha. So if alpha was rational, this would just be a periodic coloring. But since it's irrational, we get something else. But I kind of think of it as like the closest thing you could have had to a periodic coloring. So how do we know that alpha exists? So actually, factorials are pretty nice in the sense that I can actually explicitly construct alpha. So we're going to try to color the numbers according to the parity of floor of n alpha. So if it's odd, just give it colors 1. If it's even, give it color 0. And here alpha is 2 minus e over 2 minus 1 over 2e. And you might be like, well, what's e doing here? Well, e is just a summation of 1 over n factorial. So it's not so surprising that it comes up in a problem about factorials. So here what I'm claiming is not just that this coloring avoids arbitrarily long monochromatic factorials diff sequences, it actually avoids length 4. And the reason it avoids length 4 is because of this key observation here, that if I take my number alpha and I multiply it by any factorial, I'm going to get an even integer part, and I'm going to get a fractional part that's between 1/3 and 1. So if you let me use fractions mod 2, I'm always going to be between 1/3 and 1 mod 2. So why is this so useful? So let's pretend for the sake of contradiction that I really can get a monochromatic sequence of length 4. Well, all the gaps are factorials. And because of my coloring, if A1, A2, A3, and A4 are getting the same color, that means that the integer parts of A1 alpha, A2 alpha, A3 alpha, and A4 alpha have the same parity. So the consecutive differences between those, AI plus 1 alpha minus AI alpha, are of the form k factorial times alpha. So by the lemma of the proof is just some computations, it's not really involved. By the lemma, these gaps now are k factorial times alpha, so they're between 1/3 and 1 mod 2. So why does this give us what we want? So I'm just going to draw the real numbers mod 2. So this is everything with doesn't matter which side is even, which side's odd, but let's say this is everything with an even integer part, this is everything with an odd integer part, and let's pretend my whole sequence is contained in this one. So let's maybe make these dividing lines, so this is like 1/3, 2/3. So A3 alpha can't live over here. Because if A3 alpha lives over here, then I'm adding something between 1/3 and 1 mod 2. So I'm close enough to the end that I'm going to break into this region, but I'm only adding at most 1, so I can't wrap all the way back around. So A3 alpha lives in the first 2/3 here. Now, I make the claim that A2 alpha has to live in the first 1/3, because if A2 alpha lives over here, then I'm adding at least 1/3 that'll either take me to this wrong parity part, or it'll take me to the part that I just said A3 alpha is not in. And I also can't add more than 1, so I can't wrap all the way back around. So A2 alpha has to live here. And now the difference between A1 alpha and A2 alpha is between 1/3 and 1 mod 2. So I have to go back at least 1/3, and that's going to bring me, this wraps around, so it's going to take me to the wrong parity. Another way you can think about it is that essentially within this interval of length 1 mod 2, I have to stick 4 points, and it actually has to be A1 alpha, A2 alpha, A3 alpha, A4 alpha in order, because if it's not in order, let's say this is 4 and this is 3, then to get from 3 to 4, I have to wrap all the way around. So I'm going to be adding something that's in between 1 and 2 mod 2 instead of in between 0 and 1. And now since these are in order, I have 4 points that I'm putting this interval of length 1, so that one of the gaps would have to be either smaller than 1/3, or if they're all exactly 1/3, then I end up with 2 endpoints that have the wrong parity, with different parity of each other. And in general, we're not going to explicitly come up with alpha for the other dividing sets, but we will establish that one exists. So the idea is that if the underlying sequence an has no string of k consecutive 2's, we'll be able to find a coloring that avoids monochromatic DAN diff sequences of length 2 to the k plus 1. And the underlying reason for this is something similar to the dilemma we had before, which is that there's going to be some particular choice of alpha which depends on the set, such that whenever I take a number in my set D and I multiply it by alpha, I'm going to get something that's in between 1/2 to the k and 1 mod 2. So if you want to have a sequence of length 2 to the k plus 1, so this is the stuff with integer part even, the stuff with integer part odd. If it's monochromatic, I'm going to need to stuff 2 to the k plus 1 points into this interval. But also, again, we're going to have the situation where like A1 alpha, A2 alpha, A3 alpha, etc. have to be in order. Because if I have something that's out of order, then the gap has to go all the way around. So it's going to be between 1 and 2 minus epsilon mod 2, which is not ever what an element in my set times alpha looks like. And then if these are in order, I have to have it be that I'm going up by at least 1/2 to the k each time, which means I just can't fit this many points in that interval if they're that spaced apart. So, but why does this alpha exist? So I won't show all the details, but here's the basic premise, is that we're going to kind of find an alpha that works for, say, the first element of my set. So like I need some alpha such that D1 alpha has the right behavior mod 2. And then I want to find an alpha such that D1 alpha and D2 alpha have the right behavior mod 2. And then I want to find an alpha such that D1 alpha, D2 alpha, D3 alpha all have the right behavior. So the idea is you're looking at finite truncations of your set D, and you're going to look for an alpha that plays nicely with all of the elements that you're considering, and then we'll consider more and more at a time. And what we'll end up establishing is we're going to get some interval such that for any, say, gamma in that interval, D1 gamma, D2 gamma, all the way up to D2 gamma are going to satisfy this inequality. Where did it go? Where's my cursor? The inequality in the lemma is going to be true for every gamma in my interval and all the dt's up to a certain point. So we're going to like keep track of this interval of gammas that work up to 5. And then we're going to have the interval of gammas that work up to 6, and the interval of gammas that work up to 7, etc. And we're going to intersect all these intervals, and we can establish, I'm not going into the details of where this comes from, but we can get that we're going to have these nested intervals, and the lower bound for each interval is going to be at least 1/2 to the k, and the upper bound is going to be at least 1. So we can just say that if you look at the sequence of the lower bounds and the sequence of the upper bounds, these are bounded monotonic sequences. So there is going to be some limit, and that limit is what we will take to be alpha. The one thing I haven't talked about here is actually this first paragraph of the sketch of where I get these intervals from. So the idea is actually kind of working backwards. So when I construct these, what I think about is I make gamma such that like dt times gamma is between 1/2 and 1 mod 2. And then I want to further narrow things down such that dt minus 1 gamma and dt gamma are both good. And then I want to further narrow things down such that dt minus 2 times gamma, dt minus 1 times gamma, dt times gamma are all good. And you're going all the way back to starting at 1. And the idea is, so the IBTs here, you want to make it such that if dB gamma is an IBT, then dB plus 1 gamma is an IB plus 1t, and etc. So how come it's not just enough to say that I want to find like a gamma such that if it works for dB, it also works for dB plus 1? Well, essentially, I don't just want dB plus 1 gamma to be in the interval 1/2 to the k to 1. I want dB plus 1 times gamma to be in the subinterval such that if I keep multiplying it by the next AI in my sequence, it also makes the remaining dB plus 2 times gamma, dB plus 3 times gamma, etc. also end up ultimately in the desired range of 1/2 to the k to 1. So that's all I'm going to say without getting too much into the weeds with the details. But the idea is we have this recursive construction to give us a bunch of these intervals, and then we use those intervals to establish that there's a whole range of values that works for d1 up through dt, and we have such a thing for all the t's, and we take the intersection, and we're able to establish that it's a non-empty intersection. So alpha really exists. So that's it as far as my results. Just a few other things to consider about trying to establish more results about what is and what isn't too accessible. So just remember, the first thing I told you that was not too accessible of this nature was the powers of t. But the thing is, the powers of t are not accessible, or not too accessible, because of modular arithmetic reasons. It might be interesting to see if there's something that's not too accessible because of sparsity reasons. So to try to knock modular arithmetic out of the equation, we can instead look at something like d sub beta, where your set consists of floor of beta to the I, or ceiling of beta to the I, or maybe even if you prefer, like floor of like some other parameter, delta times beta to the I, which is kind of close to Fibonacci numbers, which there's some results about Fibonacci numbers. So if I had to guess here, I would think that maybe if beta is between 1 and 2, then we're going to end up with a 2 accessible set, and if beta is greater than 2, we're not. I don't really have much in the way of examples, just kind of some computations I did at some point messing around with pi and e. I didn't actually establish they weren't 2 accessible, but it sure seemed like they weren't from what I was getting. So yeah, plenty to explore with that. And then why restrict yourself to the strict exponential growth? Just in general, how sparse can we be? I talked about earlier these different sets t minus t are going to be 2 accessible, or actually are accessible for any number of colors. But t minus t isn't really sparse in the way I want it, because no matter how far you go in the sequence t minus t, you're always going to get terms that have a ratio close to 1. Like if you, for example, if you look at like the set of like I factorial minus j factorial, you're going to get a cluster of terms around each new factorial. That's really not the behavior I care about here. But I want to see is that there's like sufficient separation between every pair of terms in your sequence. So I don't have any examples yet of a set where each number is more than twice the previous and it's still 2 accessible. So that's definitely a sparsity question I'm pretty interested in. And then just one last little thing I'll throw in here. I started doing this because I gave a talk about this stuff and Patrick Schneider asked me about what if D is random. So some very preliminary results on if D is random. If you say I have some constant probability P, and I'm going to independently pick every natural number with probability P to be in my set D, then it turns out that for any number of colors, D is going to be R accessible with probability 1. And then on the flip side, there's some very clear reasons why sometimes D will not be R accessible. If the expected size of D is finite, forget about it, because a finite set is not going to ever be 2 accessible. And also, if let's say my distribution is such that I can pick odd numbers with whatever probability I want, but I pick even numbers with probability 0, well, this is just going to give me a subset of something that I already know is not 2 accessible. So that's kind of another kind of trivial reason for not being 2 accessible. But beyond that, I don't really have any reasons. And I think this is kind of wide open. So aside from the 2 obvious cases in the second bullet point, I would like to know if there's any other situations where a randomly selected D is not R accessible. Is R accessible with probability 0, or for that matter, like I think maybe there's a maybe there's some sort of 0-1 loss. So maybe if you don't satisfy certain things, you can actually show that it's going to be R accessible with probability 1. And the case that is maybe the most interesting to me, just as something concrete to start working on, is what would happen if you independently include natural numbers where n is included with probability 1 over n. I don't know what happens in that case. And that is the last question I will leave you with.
Thank you. Any questions?
Are there some results about the density version of Diffsequences? So one of the natural consequence of the Vandervaren's theorem is a similarity theorem. So is there some known class of D such that if the collection of the ground state with positive density, it contains a D diffsequences?
Yeah, this is a very good question, and it's one that I have not explored. So, I mean, if I have a set that's not 2 accessible, then we know that density 1/2 must not have been good enough because one of my colors is going to get density 1/2. But if I have a set that is 2 accessible, it doesn't mean that density 1/2 is good enough, because maybe I have some special coloring where it's actually the minority color that's the one contributing the long monochromatic sequence. So I have not looked at this. I don't know if anybody's looked at this. I mean, I don't think diffsequences are that studied in the literature, so it's quite believable that nobody would have considered a density version, but it's definitely a good question.
Thank you.
Yeah.
So I guess with these dividing sets, you have sort of a characterization if the consecutive elements of D have integer ratios.
Yeah, that's exactly what I mean by dividing set, that the consecutive elements have these integer ratios. And essentially, it's swept under the rug, but when I talk about these recursive intervals, IBT, the only way that I know how to figure out the next CBT and the next DBT in a way that doesn't lose my nice properties is to have it such that this D is a multiple of the previous D. And essentially the reason that the 2's come into play is I'm actually kind of working backwards. So I start by defining ITT to be like the interval from 1/2 to 1. And I try to work backwards all the way to I1T. And based on whether I'm even or based on whether like my AI is, or I don't know, I don't have too many indices floating around. Whatever thing I'm multiplying by to get from one D to the next D, I have two separate cases based on whether that's even or odd, and only two kind of behaves differently, which is why the arbitrarily long strings of consecutive twos thing matters. But if the D is not dividing the next D, then I don't know what happens.
So it really needs to divide it exactly? Like, what if it was like very close to an integer or?
Yeah, no, so the very close to an integer would be very interesting. But yeah, this proof very heavily rests on the exactness.
Okay.
So it's almost like the not being too accessible doesn't really have anything to do with how spread out things are. You could throw some numbers on a board that look like they're just as spread out, except for the fact they're not exactly dividing, and I wouldn't be able to tell you anything about those numbers.
So can I ask some random questions? So like when you mentioned about this count in the beginning of your talk, you talked about some counterexamples, and you said it's a bit like solving puzzles. Like to find like a non-diff sequences, just pick some like colors and so on. Now suppose I want to compute these counterexamples when, say, below your bound. So I want to find some counterexample which say that there's a coloring which doesn't have diff sequence inside the coloring. Is that can be an algorithmic questions, and then can be done very efficiently?
I mean, I can't answer anything on the theoretical side, but I can say practically how I've constructed some of these things in the past is I treated this as a linear program where, I mean, it's maybe easier when there's two colors, because when there's two colors and I'm trying to avoid sequences of length k, I have all my variables are 0 or 1 based on what color I'm using, and I just have a bunch of constraints where I take into account every possible diff sequence, and I just say the sum of the variables corresponding to this diff sequence is between 1 and k minus 1, and I put it into Groby and it spits out some values, but it's pretty computation intensive, so I haven't gotten very large examples from it. But that, and then I mean in general, I mean even if you had more than two colors, you could phrase it as a linear program, but then it might be a little bit more annoying because you maybe want to keep track of how many of each, because you can't just rely on the sum anymore. But yeah, in practice I did do some computational stuff on this, but I'm sure my code wasn't that efficient. It was just kind of trying to get some quick examples. Yeah.
So one of your questions, you were asking if there could be some what was the term? Too accessible diff sequence. Where the ratios are all strictly bigger than 2. So is it possible? So is there any upper bound on this 2 where you could hope for something like this? Like if this was 100, is it still possible to find something, or do you have some?
Yeah, that's a very good question. I put 2 here because I know that exactly 2 is possible.
Yeah.
But I don't know, for example, I don't know if 100 is impossible. I know nothing other than the fact that 2 is possible, and I haven't found anything bigger.
Okay.
Yeah, I hope the answer is like pi or something. I hope there's like some dumb threshold that's like completely unexpected.
Any other questions? If not, let's thank the speaker.